So our f of x curve is a parabola. F of x equals x squared minus 4. That's an upward facing parabola that's been shifted down 4 units, and it has x-intercepts of 2 and negative 2. You can solve that by factoring and setting equal to 0. And then our other curve, the linear curve, g of x is equal to x plus 2. That's a line of slope 1 that has a y-intercept of 2. And we can see that we're trying to find the area between these two curves. It's going to be the area of this region. From our work previously, we saw that our intersections are going to be at x equals 3 and x equals negative 2. So I can label this graph accurately to say that where x equals negative 2, that's one of the intersection places, and the other intersection place is going to be at x equals 3. And I don't need to know what the y-coordinate is, but I could plug in x equals 3 into either of these functions, and it'll give me the fact that the y-coordinate is going to be 5. And over here, the y-coordinate is going to be 0. But that's all the information that we need to find the area between these curves. We know where to start, we know where to stop, and now we know which is the top function. In this case, the top function is our red function, our g of x function. So the area between the curves is given by the integral from x equals negative 2, this intersection point, to x equals 3, this intersection point, moving from left to right. And we're going to take the top curve and then subtract away the bottom curve. So in this case, that's going to be x plus 2 minus the bottom curve, x squared minus 4 dx. And notice we could have written this as two separate integrals and taken the difference of those integrals. This just saves us a little bit of pen, a little bit of notation. So working forward, doing calculus, we can see that this is just negative x squared plus x, 2 minus negative 4 is 6 dx. And now I'm going to compute the integral using power rule, raising each of the exponents and multiplying by the reciprocal of those exponents. I end up with a first term of x cubed times negative 1/3, the negative carries on. The next term becomes 1/2 x squared, again raising the exponent by 1. And then my linear term 6 becomes 6x. The antiderivative of a constant, I'm going to multiply by x, and we evaluate this as x goes from negative 2 to 3. Inputting 3, we get negative 27 thirds plus 3 squared is 9 halves. 3 times 6 is 18. This is evaluating at our upper bound. Now we're going to subtract out the lower bound. Negative 2 to the third is negative 8 times a negative 1/3 becomes positive 8/3. Negative 2 squared becomes 4, divided by 2 is 2. And negative 2 times 6 is negative 12. And I can enter all this into my calculator. Simplifying this by combining all of these terms, I see that I get 27 halves minus, this becomes negative 22 thirds. Getting a common denominator, I end up with 125 sixths. Notice I ended up with, whoops, sorry, that's a little off the screen. Notice that I ended up with a positive result, which is what you want, because when finding the area between the two curves, you want to have a positive area. Let's look at another example. In this case, we want to find an area enclosed by 3 different curves. So to start off with this, we will need to find the intersection points, but I think that it's more informative just to go ahead and do a graph of each of these functions. So thankfully, a lot of these are pretty easy functions. We see that f of x is the function negative x, That's a line with slope -1, and I'm going to do that one in green. So this is my f of x equals -x, a y-intercept of 0. And then we have another boring function. Our g of x function is just another straight line with y-intercept of 0, this time with a slope of 1. And then we have a parabola. Let me grab another color. That's been shifted up by 2 and is facing downwards. And we see in this situation, there are actually 3 different regions that we could compute the area of. We can see that the boundary is forming this sort of triangular looking region, and it's actually sort of a curved triangle. There's also this portion that sort of looks like a portion of circle. It's not a circle because it's part of a parabola. And then this other region over here. And we're going to find the area of this top region for this problem. Without that information, you wouldn't be able to find the area enclosed by these curves. Now the key thing to notice is that depending upon where you are along this curve, your top and your bottom functions change. So notice that for the left half of this region, the top curve is our green curve, our h of x curve, 2 minus x squared, and the bottom curve is the green curve, f of x equals -x. Whereas once I cross over into this half, the bottom curve becomes the red curve, g of x. So we're actually going to need to set up 2 different integrals because the regions is going to be bounded by 2 different curves depending upon where you are. Let's set this up, but I'm not going to go ahead and evaluate it. To set it up, we need to know a couple of pieces of information, and those pieces of information are where do these curves intersect. So again, just like step 1 previously, I'm going to look for intersection points. So I need to know what is the intersection of, let's see, we did f of x in green, f of x and our parabola curve h of x. So we're going to set these 2 functions equal to one another. I see that -x is going to be set equal to the h of x curve, which is 2 minus x squared. I'm going to add x squared to this side and subtract 2, and I get x squared minus x minus 2 is equal to 0. Again, this is a quadratic. That's just because of the functions that I chose. Let's see, in this case, I am able to factor this. Again, what nice values I have. I might have to use quadratic formula for something like this, but I'm going to get 2 values that multiply together to give a -2 are going to be -2 and 1. And when I add them, I'm getting a -2 and a +1, which is -1. So this gives me solution values of x equals +2 or x equals -1. So these are the 2 intersection points between the green curve and the blue curve. Let's look back at our picture and see if that makes sense. So in our picture, we see that our green curve is intersecting our blue curve in 2 different places, and we only care about the place over here, which is the negative of these 2 values, x equals -1. And with that, that's actually all the information intersection. I'm also going to have to find the intersection of my red curve, g of x and h of x. And it turns out this is going to be a relatively straightforward computation. G of x is my function x, and h of x is -2x squared. I add the x squared, I subtract 2. X squared plus x minus 2 has to be set equal to 0. My factorization looks very similar. I get x minus 1, x plus 2, and I end up with solutions of x equals 1 or x equals -2, which graphically makes sense as well. And you can notice this by the symmetry of this figure that this intersection is at -1, and this intersection is 1. So now we're able to set up our integration now that I know that these intersection points. I also would have to solve for this intersection point, but I can see easily that f of x and g of x intersect when x equals 0. So that means, do I have enough? Yeah, I have enough room on this page. So to set up the integration, I'm going to take the left half of this region is going to be from x equals -1 to 0, because I'm only looking at that piece of it. And in that case, the upper curve is the blue h curve, 2 minus x squared. And the lower curve is my green curve, which is the curve -x. That's half the area. The other half of the area is going to be given by the curve as x goes from 0 to 1, always making sure my bounds go from left to right, of the upper curve, 2 minus x squared, minus the lower curve, x dx. Or you can also say, this is twice as much work as I need to do. If I just computed half of the region, I know that it's symmetric, so I could multiply this by 2 to be able to get the exact value. And I agree that in this case, because the figure is symmetric, we can make use of that symmetry to do half the work. For the case of this example, I'm going to finish this computation. So in this case, we're looking at the integral from -1 to 0 of -x squared minus a -x is plus x plus 2 dx plus the integral from 0 to 1 of -x squared minus x plus 2 dx. I'm going to integrate using power rule. This becomes -1/3 x cubed plus 1/2 x squared plus 2x evaluated from x equals -1 to 0. And I'm also going to add on the second integral, which is -1/3 x cubed minus 1/2 x squared plus 2x evaluated from x equals 0 to 1. Plugging in the values, I see that plugging in 0 makes everything 0. Plugging in -1, I get -1 cubed, which is -1. This becomes +1/3 plus +1/2 minus 2. This is the area of the left half of the curve. And then I'm going to add on to it the area of this half. Plugging in 1 for each of these values, I get -1/3 minus 1/2 plus 2. And these two areas should have been the same area.